The James Webb Telescope has been our eye in the sky, peering into the depths of space to bring the cosmos closer to home. Its lens has unraveled the impossible and pushed the boundaries of science. During one of its movements, the James Webb Telescope revealed an image of Proxima b, our closest exoplanet neighbor, and it was captured in detail. But something unexpected happened. What could it be? And what mysteries does the James Webb Telescope have to solve? Stay with us as we unravel the story behind this image and the sudden silence of humanity's greatest space observatory, the James Webb Telescope. The James Webb Space Telescope, JWST, was specifically designed to revolutionize the field of infrared astronomy. Equipped with cutting-edge high-resolution and high-sensitivity instruments, it surpasses the capabilities of its predecessor, the Hubble Space Telescope, by enabling the observation of objects that were previously inaccessible due to their age, distance, or faintness. This groundbreaking capability opens up a vast array of research opportunities in various areas of astronomy and cosmology. Stay to the end to find out about these discoveries and how they affected the James Webb Telescope. Astronomers have made an incredible discovery and have identified what could potentially be 6 massive galaxies from the very early stages of the universe. These objects are so incredibly large that, if confirmed, they have the potential to completely revolutionize our understanding of how galaxies form and evolve. These findings, published in the prestigious journal Nature, utilize data gathered by the powerful James Webb Space Telescope's infrared sensing instruments to provide a glimpse of what the universe looked like a staggering 13.5 billion years ago when it was just a mere 3% of its current age. What is truly mind-boggling is that these potential galaxies, which may have existed only 500 to 700 million years after the Big Bang, already exhibited a level of maturity comparable to that of our own 13-billion-year-old Milky Way galaxy today. The sheer mass of stars contained within each of these objects is estimated to be several billion times greater than that of our Sun. According to the research conducted, one of these galaxies could potentially have a mass of stars equivalent to a staggering 100 billion times that of our Sun. To put this into perspective, our Milky Way galaxy contains a mass of stars roughly equivalent to about 60 billion suns. This discovery serves as a stark reminder of the immense scale and complexity of the universe, offering a tantalizing glimpse into the early stages of galactic evolution and challenging our preconceived notions of how galaxies come into being. The implications of this research are profound, and what happened next after its discovery with the James Webb Telescope is something that will shock you. When Erica Nelson, an astrophysicist at the University of Colorado Boulder and a co-author of the study, expressed her surprise at the discovery of galaxies with as many stars as the Milky Way appearing so quickly, she highlighted the incredible nature of these findings. She found an exoplanet, which is a celestial body located outside of our solar system, that has been discovered in the Centaurus B star system. This exoplanet is an incredible 11 times more massive than Jupiter, the largest planet in our solar system. The Centaurus B star system is classified as a young binary system, meaning that it consists of 2 stars orbiting around a common center of mass. This particular star system is located approximately 3,125 light-years away from Earth, making it quite a distance from our planet. Centaurus B, which has recently been discovered, is one of the most massive planets ever identified. This planet orbits around 2 stars that are significantly heavier than our Sun, with a combined mass that is 6 to 10 times greater. This makes the Centaurus system the most massive one in which a planet has been observed. Additionally, Centaurus B is known to be the hottest star system that hosts a planet. The 2 Centaurus B stars, also known as Centaurus A and Centaurus B, are relatively young in cosmic terms, being only around 15 million years old. In comparison, our Sun, a G-type main sequence star, has been shining for over 4.5 billion years, making it significantly more mature. Despite their youth, the Centaurus stars have already gone through various stages of stellar evolution, shaping their characteristics and influencing their future development. The researchers were initially anticipating the discovery of small, young galaxies in the early stages of the universe's development. Evalab, the lead researcher of the study from Swinburne University of Technology in Australia, described these galaxies as monsters that seem to have rapidly matured. The mystery of how these galaxies were able to reach such a level of maturity at such a fast pace remains unanswered, leaving scientists intrigued and eager to delve deeper into this phenomenon. They have discovered something more intriguing. They discovered Proxima Centauri near the Centaurus B star. Proxima Centauri is a red dwarf star located just over 4 light-years away from Earth and is known for its frequent and intense flares of radiation. These powerful bursts of stellar energy have the potential to significantly impact the conditions on any planet orbiting the star. The radiation emitted during these flares could have a detrimental effect on the atmosphere and surface of Proxima Centauri b, potentially stripping away the protective layer of gases that allow life to thrive. The intense radiation from Proxima Centauri flares could also pose a significant threat to any potential life forms that may exist on the planet. Exposing organisms to harmful levels of radiation could hinder their ability to survive and reproduce, making it challenging for complex life to evolve on Proxima Centauri b. Despite these challenges, the possibility of Proxima Centauri b hosting an environment conducive to life has captured the interest and excitement of scientists and astrobiologists alike. The potential for liquid water to exist on the planet, along with its location within the habitable zone of its star, makes Proxima Centauri a tantalizing target for further study. Now, using sophisticated computer models that are similar to the ones used to analyze climate change here on Earth, scientists have discovered that Proxima Centauri b can maintain vast expanses of liquid water on its surface across various scenarios. This exciting development significantly bolsters the chances of the exoplanet being able to support diverse forms of life. Despite its proximity, scientists still know very little about Proxima Centauri's planetary companion. What is known is that the planet has a mass of at least 1.3 times that of Earth and orbits its parent star every 11 days. This lack of information presents a unique challenge for researchers eager to learn more about this intriguing celestial body. This leads us to a question. Is the atmosphere on Proxima Centauri conducive to life? Proxima Centauri b, the exoplanet that orbits within its star's habitable zone, is positioned at an optimal distance from its parent star to receive sufficient starlight to maintain a surface temperature above the freezing point of water. This crucial placement within the habitable zone implies that there is potential for liquid water to exist on the planet's surface because, as we know, water is a key factor in supporting life. However, it is noteworthy to mention that because of Proxima Centauri's orbit, which is close to its star, the planet may have become tidally locked as a result of the intense gravitational forces at play. Tidal locking means that one side of the planet always faces its star, while the other remains in perpetual darkness. A phenomenon similar to the Moon's relationship with Earth, where only one side is visible from our vantage point. There are two likely scenarios for the atmosphere of Proxima Centauri b. In one case, it is possible that the planet's water condensed and the hydrogen was lost to space, resulting in only oxygen or carbon dioxide remaining in the atmosphere after the planet's early history. On the other hand, it is also possible that Proxima Centauri b had a primordial hydrogen atmosphere or formed farther away from its star, which would have limited the escape of water. This suggests that Proxima Centauri b may have retained its water beyond its early history. If indeed an atmosphere exists on the planet, it is likely to contain oxygen-bearing gases such as oxygen and carbon dioxide. When combined with the star's magnetic activity, these gases could lead to the formation of auroras that might be visible from Earth and make the planet look like it has a magnetic field. But that's not all. Climate models, including general circulation models used for Earth's climate, have been utilized to simulate the atmospheric properties of Proxima Centauri b. These models take into account factors such as whether the planet is tidally locked, the presence of water and carbon dioxide, and various other variables. Different scenarios are possible for the conditions on Proxima Centauri b. It could be a planet covered in ice, either partially or completely. Alternatively, it might be a large planet with vast oceans or smaller bodies of water. There is also the possibility of regions with only dry land. Some models even suggest the existence of unique features like eyeballs or lobster-shaped areas with liquid water resembling claws sprouting from the equator. Moreover, scientists speculate about a subsurface ocean beneath a thin, slushy ice cover that may vary in thickness across different locations. By using climate models, scientists have been able to explore the potential conditions on Proxima Centauri b and consider the wide range of possibilities for this distant exoplanet. But then, is Proxima Centauri b habitable? You see, Proxima Centauri b faces a challenge when it comes to its habitability due to the strong UV radiation and X-rays emitted by its star, Proxima Centauri. This planet receives much higher levels of radiation, especially X-rays, compared to Earth. In the past, it might have even received higher amounts, resulting in cumulative X-UV radiation that is 7 to 16 times greater than what Earth experiences. This radiation can cause the atmosphere to evaporate as hydrogen absorbs it and becomes trapped, eventually reaching a point where it can escape the planet's gravitational pull. Moreover, the radiation can split water into hydrogen and oxygen, with the hydrogen being heated in the planet's outer atmosphere until it escapes. This process can also lead to the loss of other elements like oxygen and nitrogen. While nitrogen and carbon dioxide can escape on their own, it is unlikely to significantly reduce their presence. When it comes to a planet similar to Earth, you won't believe the next one. Stellar winds and coronal mass ejections pose a significantly greater danger to an atmosphere. The impact of stellar wind on Proxima Centauri b could be 4 to 80 times greater than that on Earth, exerting a pressure that is approximately 10,000 times stronger than the Sun's stellar wind. This heightened intensity of UV and X-ray radiation has the potential to propel the planet's atmosphere beyond the reach of its magnetic field, thereby amplifying the loss caused by stellar wind and mass ejections. If the star's gravitational pull causes the planet to always face the same side towards it, there is a possibility that the atmosphere could collapse on the side of the planet that is in darkness. This is especially concerning for a planet with a dominant carbon dioxide atmosphere, although the presence of carbon dioxide glaciers could potentially recycle the atmosphere. In contrast to stars similar to our Sun, the habitable zone of Proxima Centauri would have been located farther away during the early stages of the system's formation when the star was in its pre-main sequence stage. In the case of Proxima Centauri, if we assume that the planet formed in its current orbit, it could have spent up to 180 million years being too close to its star for water to condense. As a result, Proxima Centauri b may have experienced a runaway greenhouse effect, causing its water to evaporate into steam. This steam would then have been split into hydrogen and oxygen by UV radiation, leading to the loss of hydrogen and any water, similar to what is believed to have occurred on Venus. Shocking, right? Although the specifics of impact events on Proxima Centauri b are currently unknown and speculative, they have the potential to destabilize the planet's atmosphere and cause the boiling off of its oceans. However, Proxima Centauri b, which is covered in ice and has an ocean beneath its surface, is expected to have icy volcano-like activity similar to Jupiter's moon. This icy volcanic activity would create a thin outer layer similar to Europa, another moon of Jupiter. Even if Proxima Centauri b lost its original atmosphere, volcanic activity could eventually rebuild it. The new atmosphere would likely have carbon dioxide, which would make it more stable than an atmosphere similar to Earth's, especially with the presence of an ocean, depending on the size of the ocean as well as the mass and composition of the atmosphere. If there are exocomets present, they could bring water to Proxima Centauri b through impacts. Is there water on Proxima Centauri b? If rumors have it, it might be full of ice. Scientists have been studying how water could be delivered to Proxima Centauri b, which is a developing planet. It is still unclear how much water this planet actually received. One study by Rebus in 2016 suggests that Proxima Centauri b may have lost no more than the amount of water in one Earth ocean. However, later research indicates that the amount of water lost could be much greater. Another study by Avidan et al. In 2017 concluded that the planet's atmosphere could be lost within 10 million years. These estimates are uncertain because they depend on the initial mass of the atmosphere. Another thought-provoking question that has been on our minds is the possibility that there could be inhabitants on Proxima Centauri b. In the field of studying exoplanets, the term habitability typically refers to the potential presence of liquid water on a planet's surface. For exoplanet life to thrive, it is generally understood that both liquid water and an atmosphere are necessary conditions for habitability. Detecting life that exists solely in the subsurface of a planet, like in Europa's subsurface ocean within our own solar system, would be challenging from a distance. However, it could serve as a possible model for life in a rigid, ocean-covered world like Proxima Centauri b. Proxima Centauri b's habitability is a hot topic with a few things to think about. Proxima Centauri's activity and tidal locking could make it hard for life to thrive there. UV radiation on Proxima Centauri b is colder and might not interact much with organic compounds, which could mean less ozone. But too much stellar activity could break down the ozone layer, leading to dangerous levels of UV radiation. Depending on its orbit, Proxima Centauri b might sometimes be outside the habitable zone. Oxygen and carbon monoxide could build up in the atmosphere, reaching toxic levels. However, high oxygen levels could help complex organisms evolve. Tides on a planet with oceans could cause flooding and drying, triggering chemical reactions that support life. Tides could also help develop biological rhythms like the day-night cycle, mix oceans, distribute nutrients, and encourage the growth of marine organisms like red tides. The next one will shock you. Proxima Centauri has a much longer lifespan than the Sun. In fact, they can live for many times longer than the estimated age of the universe. This means that there is plenty of time for life to develop. However, the radiation emitted by Proxima Centauri is not ideal for oxygen-generating photosynthesis. Instead, it is more suitable for a different type called anoxygenic photosynthesis. Scientists are still unsure how to detect life that depends on anoxygenic photosynthesis. In a study conducted in 2017, it was estimated that the productivity of Proxima Centauri b's ecosystem based on photosynthesis may only be about 20% of Earth's. But how did the James Webb Telescope discover the Centauri b star? Before we delve into what led to its shutting down, let's look at the amazing features of the James Webb Telescope. The James Webb Space Telescope, known as Webb or JWST, stands as a groundbreaking space observatory with unparalleled capabilities. Its mission is to transform the field of astronomy, pushing the boundaries of our knowledge, from the formation of stars to the evolution of galaxies, and even delving into the mysteries of the very first galaxies that emerged in the universe. With a focus on exploring the intricate properties of planetary systems, JWST promises to unveil a wealth of new information and scientific discoveries. The telescope was named after James Webb, and it represents a significant milestone in his legacy. James Webb's leadership at NASA during a crucial period of space exploration laid the foundation for groundbreaking projects like the Hubble Space Telescope and the Mars rovers. Despite its ambitious goals and potential, the road to launching the JWST was fraught with challenges. Originally proposed as a $1 billion project set to launch in 2017, the mission underwent significant delays and setbacks that ultimately led to a substantial increase in its budget. The final cost of the project ballooned to $10 billion, and the long-awaited launch finally took place in 2021 after years of meticulous planning and preparation. What comes next will surprise you. Telescopes on Earth face a significant challenge when it comes to observing the skies: the interference caused by the atmosphere. This is a major issue even for telescopes located far from the light pollution of cities, as the atmosphere contains moisture that can both attenuate and distort the signals received by the instruments. To combat this problem, astronomers often choose to place their observatories in high-altitude locations, such as Mauna Kea in Hawaii. Additionally, they seek out dry environments, such as those found in the southwest U.S., where atmospheric interference is minimized. Ideally, astronomers aim to locate their observatories in spots that are both high and dry, like the high desert of the Atacama in northern Chile. By selecting these optimal locations, astronomers can maximize the effectiveness of their telescopes and obtain clearer, more accurate observations of the cosmos. Regardless of how high or dry you ascend, the Earth's atmosphere will continue to present challenges. However, there exists an alternative method to overcome these limitations: placing your telescope in space, where the absence of atmosphere prevents image distortion. This is the key reason behind the success of Hubble and similar telescopes. With any luck, JWST will soon join the ranks of space telescopes. The earlier telescope, the Hubble Space Telescope, was a beacon of discovery in the field of astronomy for 3 decades. It provided stunning images and groundbreaking research that have reshaped our understanding of the cosmos. From capturing the birth of stars to uncovering the mysteries of black holes, Hubble was an invaluable tool for scientists around the world. However, as technology has advanced and our thirst for knowledge has grown, the need for a more powerful telescope has become apparent. When the James Webb Space Telescope, JWST, was built, the next-generation space observatory prepared to launch into the near future. With a mirror more than twice the size of Hubble's, JWST promised to push the boundaries of what we know about the universe. Its infrared capabilities were built to allow astronomers to see further back in time than ever before, peering into the early days of the universe and unlocking secrets that have long been hidden from view. It doesn't end here. The James Webb Space Telescope, JWST, has a primary goal of advancing the study of exoplanets, which are planets outside of our solar system. Astronomers were eager to utilize JWST to gain a better understanding of how stars form and evolve, and how it ultimately led to the development of planetary systems. By using JWST, scientists hope to delve deeper into these planetary systems, allowing them to observe the atmospheres of exoplanets with unprecedented detail. Furthermore, JWST was built to enable researchers to search for potential signs of life, known as biosignatures, within these distant worlds. With its advanced capabilities, JWST has the potential to revolutionize our understanding of the universe and the possibility of life beyond Earth. JWST's most valuable component is its mirror, which measures 21.3 feet, 6.5 meters, across, making it the largest mirror ever sent into space. This significantly surpasses the 7.8-foot, 2.4-meter mirror of the Hubble Space Telescope. The mirror, known as the optical telescope element, OT, is crafted from beryllium with a gold coating and consists of 18 hexagonal sections, each comparable in size to a large table. To ensure precision, over 100 motors support the mirror for delicate adjustments. The creation of the mirror presented a formidable task for JWST's engineers, as even minor flaws could severely impact the telescope's observational capabilities. Ball Aerospace and Technologies was responsible for constructing the mirror, which was then assembled at NASA's Goddard Space Flight Center in Maryland. Hubble mostly looks at things in visible light, but JWST will focus on longer wavelengths, especially in the infrared. Scientists believe this will help the telescope see objects that are farther away from us, as the light from these objects gets redshifted into longer wavelengths. JWST has 4 instruments that are made to detect infrared signals very sensitively. These instruments will be inside a spacecraft bus, which is a box mainly made of graphite composite. The bus also holds JWST's thrusters, computer, and communications equipment, making it the heart and brain of the telescope. To protect the bus, there is a huge sun shield and a cryocooler that uses helium to keep the components at a super cold 37 Kelvin, which is minus 393 degrees Fahrenheit or minus 236 degrees Celsius. The James Webb Telescope can also look at things in the solar system from a really big angle away from the sun, like more than 85 degrees. It can see things like Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, their moons, and even comets, asteroids, and small planets that are far away from Mars. Webb is good at seeing things in the near-infrared and mid-infrared parts of light, so it can see almost all the objects in the Kuiper belt that we know about. It can also look at things that come up unexpectedly, like supernovae and gamma-ray bursts, within just 48 hours of deciding to do so. How were 6 unknown galaxies spotted by the JWST, and how did it open our eyes to the origin of life? The James Webb Space Telescope, with its state-of-the-art technology, has provided us with a glimpse of the distant universe. In a recent discovery, astronomers have observed 6 galaxies that have defied our current understanding of cosmological theories. These galaxies, which took shape within the first 700 million years of the universe's existence, appear to be unexpectedly massive, up to 100 times larger than what was previously thought possible. According to astronomer Evolab and his team, the combined mass of the stars in these galaxies surpasses the total amount of mass believed to be present in the universe during that early period. This revelation has left scientists puzzled and intrigued, as it suggests that there may be unknown forces or processes at play in the formation and evolution of galaxies in the early universe. The telescope, officially known as the James Webb Space Telescope, JWST, made its groundbreaking debut by unveiling its first glimpse of the early cosmos in July 2022. As reported on November 7, 2022, almost immediately after the release of these awe-inspiring images, Lab and his team of researchers were able to identify approximately 12 celestial objects that appeared exceptionally luminous and characterized by a deep red hue. This distinctive coloration hinted at the possibility that these objects were not only massive in size, but also situated at a significant distance from Earth. The brightness and redness of these objects make them unmistakable. They truly stand out upon initial observation of the images, remarked astrophysicist Erica Nelson from the esteemed University of Colorado Boulder. Measuring the amount of light each object emits in various wavelengths can provide valuable insights for astronomers. By analyzing the light emitted by galaxies, scientists can estimate their distance and determine the number of stars they contain. In a recent study, Nelson, Lab, and their colleagues identified 6 objects that appear to have formed no later than 700 million years after the Big Bang. These galaxies are estimated to contain up to 10 billion times the mass of our Sun and stars, with one of them possibly holding the mass of 100 billion suns. Are you surprised? The rapid formation of galaxies with such massive star populations challenges the current understanding of galaxy evolution. Our Milky Way galaxy, which has had over 13 billion years to evolve, contains approximately 60 billion suns worth of stars. The existence of these young massive galaxies is astounding and raises questions about the mechanisms that drive their formation. Also, scientists' finding of the 6 galaxies from the early universe helped them learn about what the universe was like right after the Big Bang.